Warm welcome to everyone who's joined us at Battery Day 2023 today. As you know, it's been a long day for all of us, but thank you anyway for joining. And welcome to everyone who's watching the recording as well. I hope everyone's enjoying the Battery Day so far. We had an excellent line of speakers and a lot of insightful discussions flowing in. Um, but today, our deep dive is going to be on sodium ion batteries, and we have amongst us Harshita Lohani. I'll quickly introduce her as the speaker, and then the floor is all yours, Harshita. So Harshita Lohani is a senior PhD research scholar working in the field of battery chemistry from the IIT Bombay. Throughout her career, she has dwelled into the intricacies of various battery chemistries, including the well-known lithium-ion technology, the promising sodium-ion alternatives, and cutting-edge metal and solid-state batteries. She boasts an impressive academic journey with a wealth of experience spanning over 3 to 4 years in the realm of battery research. She's currently engaged in the study of electrode electrolyte interfaces with sodium ion and metal batteries to the innovative approach of electrolyte engineering. Her contribution to the field of batteries is demonstrated by her remarkable publication record, which boasts three international journal publications and book all chapters, all dedicated to the advancement of energy storage. So we're extremely glad to have Harshita with us today, speaking on sodium-ion batteries. She'll be talk about the history of sodium-ion batteries, what components make them work, how they are comparable to regular lithium-ion batteries, and cost and performance. The attractive feature of shipping and storing sodium-ion cells at zero energy as well. And she'll also take a glance at into the latest advancements achieved by industrial pioneers in the battery field. So without any more further ado, I'm just going to hand it over to Harshita, who's going to take over the stage. Thank you, Harshita, for joining,
Uh,
and the floor is yours.
Thank you, Priyal, for such a nice and generous introduction of mine. So, without taking much more time, let's take a deep dive into sodium and batteries today. So, this is me. I am Harshita Lohani, and I'm a PhD research scholar at IIT Bombay. My research interests include sodium ion batteries, sodium metal batteries, and currently I'm working to study the electrode electrolyte interfaces through electrolyte engineering for improving the performance of sodium ion and sodium metal batteries. So, this is my LinkedIn URL. If you want, you can join me. Now, coming to the outline of my presentation today. So, I'll first give a brief introduction why we actually need these sodium ion batteries. And then I'll move towards a overview about the history of the development of sodium ion batteries, what are their key components and materials. And then I'll quickly go over the advantages of sodium ion batteries over lithium ion and existing lead acid batteries, their comparison on cost, and then I'll talk about the one of the most interesting feature of sodium ion battery, which is shipping and storage of sodium ion batteries at 0 volt. And then we will also see some of the key players in this field and what are the cell specifications that they have given and what are their current and projected manufacturing for the sodium ion batteries. And then I'll finally wrap up my presentation by giving some insights on the industrial advancements which is happening in this field. So, coming to the introduction, so sodium ion batteries work exactly in the similar way like the lithium ion battery works. It has a positive electrode, negative electrode, and an electrolyte. So, during the charge of the battery, sodium atom removes one electron and that electron goes to the outer circuit while the sodium ion moves from the anode from the cathode to the anode side and takes the electron and gets stored there, and the reverse process happens in the opposite charge process, discharge process. Now, what is the difference then between the sodium ion and lithium ion batteries? Why we are discussing them at all? So here comes the graph. So as compared to lithium, which is the 33rd abundant element on Earth crust, sodium is the seventh most abundant element on Earth. And it has even distribution of sodium worldwide. It is comparatively cheaper to some of the lithium and battery chemistries that I will discuss in my later slides. And they are safer, especially when we talk about their storage and transportation at 0 volt charge. That also I'll discuss in my later slides. Now, if we see the trend of the cost of sodium carbonate and lithium carbonate from the year 2017 to the year 2022, so here we can clearly see that the amount of lithium carbonate is increasing highly, like especially after the year 2020, because of the high demand of the lithium raw materials in the batteries in the electric vehicles. But if you see the trend for the sodium carbonate, so the price is almost constant and it is almost half of the price for the lithium carbonate. So this makes this technology very interesting in terms of cost, and also it is like in some of the battery chemistries, it is like comparable to the chemistries of lithium and batteries. Now, earlier, people were focusing on sodium-ion batteries to be used them in stationary storage applications, especially for renewable energy storage and power backup for data and telecom companies, for grid-scale energy storage. But as the performance of these sodium-ion cells are improving with the years, so now people are shifting towards using these sodium-ion batteries also in the two-wheeler and four-wheeler compact electric vehicles. But the problem, and the only one problem with this technology, is its low energy density. Now, if we talk about the history of sodium-ion batteries, so it started in year 1976 when one of the scientists when this demonstrated sodium-ion intercalation in a titanium disulfide anode using sodium amalgam as a counter electrode and sodium iodide in a non-aqueous electrolyte as an electrolyte system. Then, in 1980, Newman and Clement, two scientists, demonstrated same titanium disulfide as an anode for sodium ion storage, but this time against sodium metal. So basically, they have made a sodium half cell for the first time. After that, in 1987, Shacklet and others of Elite Signal demonstrated the viability of first sodium-ion battery rocking chair mechanism, where they used sodium cobalt oxide as a cathode and a polymer-based anode. This polymer-based anode was then replaced by a coke-derived anode by Doef and others in 1993. So this was actually the first rocking chair type system where carbon-based anode was used in a sodium-ion fuel cell. Now, in 2000, finally, Stephen and Dan were able to found a anode, which is also considered as a state-of-the-art anode for sodium-ion batteries today, which is a disordered type of carbon known as the hard carbon, and which gives a capacity of 300 milliampere hour per gram, which is very close to the capacity which graphite gives for lithium-ion batteries, which is 375 milliampere hour per gram, theoretically. Then in 2002, Barker and others demonstrated their first rocking chair sodium-ion battery using hard carbon anode in non-aqueous battery system. After that, this technology was actually patented by Valence Technology, and then many researches were keep on happening to increase the performance, cycle life, and safety of these batteries. And today, in the year 2023, we are here at the stage of prototyping and commercializing of these sodium-ion batteries. Now, what are the key components and materials which make these sodium-ion batteries? So, if we see a comparison between sodium-ion and lithium-ion batteries, so the major difference is for sodium-ion batteries, we can use aluminium as a current collector on both the sides of anode and cathode, which is not the case for lithium-ion batteries because aluminium can form alloy with lithium-ion at especially at low potentials where anode works. And other than that, there are different type of cathode materials that are used in sodium-ion batteries, which include Prussian white, layered oxide, polyanionic cathodes. However, there is not much literature or not much research on the separator and electrolyte part of the sodium-ion battery. So people have directly taken such systems which they were using for the lithium-ion batteries, including the sodium counterparts. Now, if we talk about the cathode material, so these three cathodes are basically the most researched and most viable candidates in the current sodium-ion prototype cells. So, what are the pros and cons these cathodes have? We will discuss it about them one by one. So, first let's start with the Prussian white. So, the pros which associated with this type of cathode is it has a high structural stability, and because of which it can provide a very good cycle life and a power capability to the sodium ion system. But the disadvantages with this cathode is its moderate gravimetric energy density and a poor volumetric energy density. Now, coming to the layered oxide cathodes, so it has an advantages of high gravimetric energy density, high volumetric energy density, but they suffer a huge structural changes during cycling, it means during charge and discharge of a sodium ion cell, and because of which we are limited with the cycle number with these type of cathodes. Now, the third candidate is the polyanionic type cathodes, and it has an advantage of high potential of 3.7 volt, but again, it is limited because here vanadium is the main redox component and which is considered as a very expensive and toxic element. Now, if we talk about the companies which are working in on these type of cathodes, so CATL and Netron Energy, they basically are working on Prussian white cathodes, and there are companies which are like most of the companies are actually now working on layered oxide cathodes. These include Faradion, Heina Battery, S-Hold, Lyphon, and then there are some companies who are focusing on polyanionic type of cathodes. So these are Tiamat, Cody, EVE, and Junism. Now, we have talked about the cathode. Now, if we talk about the anode, so there are very different type of materials that have been researched for using anode in sodium-ion batteries, but most of them actually failed because of their one disadvantage or the other. And the most suitable candidate for anode right now is still intercalation-based type of materials, which is nothing but the disordered hard carbon material, because they render a better cycle life, they are environment friendly, cost effective, and they have a low specific but they suffer a low specific capacity. There are other materials which are good in terms of the specific capacity, but they suffer huge volumetric changes during charging and discharging of the battery, and therefore the cycle life of the battery is very much limited in these type of materials. So but the second generation of sodium ion batteries will definitely employ these alloy on conversion type of materials which have a high specific capacity compared to intercalation based materials. And if we talk about the electrolyte part, so there are basically four type of classes for the electrolyte that are being used in sodium ion batteries right now. So these include non-aqueous liquid electrolyte, aqueous liquid electrolyte, gel polymer electrolyte, and solid state electrolyte. But the commercial or we can say the prototype cells which are available right now, they mostly use non-aqueous liquid electrolyte in their prototype cells. Now, what advantages these batteries have over lithium ion and lead acid technology? So, these are the four basic advantages that we can consider. Like, these are actually the advantages of sodium ion batteries over lithium ion and lead acid technology. So, the first include the fast charge and discharge capability of these systems. So, there are few startups on sodium ion batteries which have shown that 15-minute charge is possible with sodium ion batteries. And the other thing is the wide temperature operation means they can perform well at lower and higher temperature compared to lithium ion and lead acid technology. They are safer, especially when we talk about the storage and transportation of these batteries at 0 volt or 0% state of charge that I'll discuss in the next slides. And then if we have a comparison between the cost, safety, cycle life, and the gravimetric energy density or the temperature performance of these batteries with LFP or NMC based lithium ion chemistries or lead acid chemistries, then we can see that they are actually taking a lead in terms of the cycle life, low temperature performance, and cost if we compare them with the existing battery technologies. And also, if we see like what can be the potential application areas where sodium ion batteries can be used by replacing the existing lithium ion or lead acid battery technologies. So these include firstly the diesel generators, though the cost of implications of diesel generators is low initially, but their maintenance cost is very high if we see them for a long run. But sodium ion batteries can actually replace diesel generators if we have a better energy density in the coming years for the next generation of sodium ion prototype cells. And other than that, lead acid and lithium ion batteries have a major shares in the UPS and telecom sectors, grid and home solar energy storage. So these type of systems are can be replaced if we have better and a high energy dense sodium ion batteries. Now, if we compare the cost material wise, then we can see that like most of the sodium ion batteries have a lower material cost than NMC based lithium ion chemistries. But there are few chemistries like NaMnO2 or NaNiMn, MgTiO2. These type of cathodes have actually lower material cost than LFP based systems as well. So we can say that they are cost effective than NMC based systems, and they are like becoming cost effective if we say like for the lithium LFP based systems. Uh, Now, if we compare the battery cost of different chemistries of sodium ion batteries with LFP and NMC 811 batteries, which have a like major market share in right now, so we can see like the Prussian white chemistry have a very lower price as compared to the LFP and NMC both. Layered oxide and polyanionic are pretty much comparable to LFP, but they have around 20 to 30% lower price than NMC 811. Now, another feature which is like very interesting for me, and I think this is one of the best advantage of sodium ion chemistry as well, that it can be shipped and stored at 0 volt or 0% state of charge. So currently, lithium ion batteries can be stored at 30% state of charge, which are the international standards. Because after that, like there are chances of fires or like the battery discharge can take place and can cause potential different accidents when we transport or store them. So, but in case of sodium ion batteries, this is not the case. Then, what is the difference between the two chemistry? Like, why shipping and storage can be possible for sodium ion batteries at 0% state of charge? Is because we can use aluminium on the cathode as well as on the anode side. And if we use aluminium on the anode side, so when we charge our cell or discharge our cell, the potential of this aluminium can go uh, can go till the limit where there will be no oxidation or reduction of that current collected. However, if we see like for the lithium ion batteries, if we discharge a full cell, a lithium ion full cell, the anode potential keeps on increasing, and when it reaches above 3 volt, copper oxidizes and it starts coming from the anode side and it starts depositing on the other cathode side. So in that way, if we see that the performance of the lithium ion fuel cell degrades if we discharge them below 30% state of charge, or if we take them to the 0 volt or zero energy. With sodium ion cells have the potential that they can be discharged to 0 volt or even less than that. So Faradion, which is like one of the pioneer company in this field, so they have tested sodium ion cells in the at 0 volt storage for 6 months, and then they have compared their performance with their short circuited cells and the normal cells which were not shorted, and they found that there was very less or minimal difference between the performance of the two cells. And they confirmed that sodium ion cells can be shipped and stored at 0 volt or 0% state of charge, and this makes this battery safer, especially when we transport or store them in an area. Now, who are the key players in this field? So, mostly the companies are in China. So, CATL is one of the leading company in China who are working on the sodium ion battery development. Then after that, Haina Battery, Lifeon, S-Volt are the major companies. But there are few other players in Europe, UK, and India as well. So Tiamat from France, Altres from Sweden, and then Netron Energy in US, Faradion in UK, and Reliance Industries in India are also one of the major key players in this field. If we see the stage of development of sodium ion batteries, then we can see that Faradion, Haina Battery, Netron Energy, and EMT Power are already at the stage of industrialization of these batteries now. But CATL, Tiamat, Altres are transitioning into the commercialization of their prototype sodium ion cells. And there are some companies which are still at the stage of research, which are Indie Energy or Sodion Energy. The cell specifications, which have been mentioned by various reports of these companies, these are here. So here you can see like CATL and Faradion are leading in terms of the specific energy, so which is around 160 watt-hour per kg. And Tiamat, Zunism, and Haina Battery are leading in the cycle life. So they have shown the cycle life of more than 5,000 till 6,000 for the Tiamat sodium and prototype cells. And if we talk about their comparison, like the comparison of these sodium ion cells with the currently existing LFP based lithium ion cells, then we can find that the sodium ion cells are actually comparable in performance to the LFP based lithium ion cells, where graphite has been used as an anode on one side. Whereas, like the LFP based cells, where silicon, which is the next generation anode, has been used on the anode side, they have a very high energy density. And if we see the Faradion prototype cells, which are in testing underway, so they are claiming that they can reach till 190 watt-hour per kg of their at the cell level. Then these cells can actually go far away in the performance as compared to the LFP-based graphite cells as well. Now, if we see the overview of these top four sodium ion battery players, then Faradion, Tiamat, Haina Battery, and Netron Energy are taking the lead. And if we see, like the gravimetric energy density is highest right now for Faradion, which is 160 watt-hour per kg. They have a nominal operating voltage of 3.2 volt, and they have reported a cycle life till 3,000 cycles. And if we see the summary of the current and globally projected sodium ion battery manufacturing capacity, so the bigger players like Haina Battery, CATL, and Netron Energy, Tiamat, and Faradion, they are actually currently having a production facility which can produce like 1 to 10 gigawatt hour of sodium ion battery cells. But if we see the projection which they have given in their reports, so the capacity of sodium ion battery manufacturing can reach up to 20 watt-hour per kg till the year 2030. These are some of the commercial products of the sodium ion technology, which these big players have actually started demonstrating in the actual systems. So Netron Energy has a 12.5 kilowatt hour battery racks, which they are using in the data centers in US. And Faradion has launched a 11.5 kilowatt hour residential energy storage units in Australia. Aeon are selling their 30 ampere hour sodium ion pouch cells to the Aeon group for checking their viability for mobile solar energy storage. And Haina Battery already has a 1 megawatt hour battery system for stationary solar energy storage in China. As I said that initially people were thinking of using these batteries for the stationary energy storage only, but since the performance of these batteries are now becoming comparable to the LFP batteries of the lithium-ion battery chemistries, so people are now thinking to use these batteries in low to moderate range electric vehicles as well. So this graph shows the driving range versus battery pack capacity. So it is comparing basically three different chemistries: NMC-based lithium-ion chemistries, LFP-based lithium-ion batteries, and the third one is the hypothetical sodium-ion battery pack if we consider the current existing sodium-ion cell specifications. So here you can see like NMC and NCA based electric vehicle battery packs are obviously having a very high battery pack energy density, which is around, like greater than 250 watt hour per kg, and they have a long miles for the driving range, which is like more than 280 to 350 miles. But if we see the LFP or the sodium ion hypothetical sodium ion based EV battery packs, so even with 120 watt hour per kg of the sodium ion pack, we can go up to 240 miles, and which is like very close to the LFP BYD hand battery pack. And BYD has actually used the cell to pack format to achieve this 140 watt hour per kg at the pack level from a 165 watt hour per kg at the cell level LFP based lithium ion cell. And if similar type of format, similar type of battery pack engineering could be done for sodium ion cells as well, then these batteries can also achieve a very good mile range, especially which is like advantageous for low to moderate range electric vehicles. This cell to pack level actually reduced a lot of inactive material which is present in the battery pack. So they are basically going directly from the cell level to the pack level, and they are eliminating the module formation in between. And because of that, they are making a long cells which are around 600 long, and they are directly placing it to make the battery packs. And this is actually easier for sodium ion cells because they are less prone to have the thermal runaways at higher temperatures, and they have a very good like wide temperature range. So this type of engineering is more easier for the sodium ion cells if we apply it, the cell to pack technology of the BYD to these sodium ion cells. Now, if we talk about the actual products which are demonstrated for these sodium ion battery packs, so this is one of the first Seol E10X sodium ion battery pack electric vehicle, four-wheeler electric vehicle, which has an energy density of 120 watt hour per kg. This is actually launched by Hyna Battery in collaboration with their joint venture, which is Jack. This is one of the joint venture of them, and they are claiming that this four-wheeler vehicle can go up to 252 kilometers and can support fast charging of 3C to 4C. And the battery pack uses the cells which has an energy density of 140 watt hour per kg, which is like currently existing energy density for the sodium ion cells by Faraday and the others. And if we see the format of the sodium ion cells that has been used in this Seol E10X, so these are 32140 format sodium ion cells, means 32 mm in diameter and 140 mm long. So these are the cylindrical cells which they have used in this battery pack. Now, CATL and BYD are actually moving for making a hybrid battery pack where they will take an advantage of wide operation window from sodium ion cells, and they will take an advantage of better energy density from lithium ion cells. And they are planning to make the hybrid battery packs and are planning to apply these packs in some of their four-wheeler models. I will show this thing this through this very nice video where this man is talking about the same thing, the hybrid technology. Okay, so with this, I want to end my presentation. I want to thank Battery Associates for giving this platform for speaking today, like the deep dive on sodium and batteries, which is one of the favorite topic of mine. And now I am open for Q&A.
Perfect. Thank you very much, Arshita. I see questions flowing in now, and great appreciation for your presentation as well. So I'm just going to talk about the first
Sure.
question we have from Gerard. How does this round
Yeah.
trip efficiency of sodium ion compare to LFP batteries? And is there any real world data published that evaluates the efficiency, as this is typically lower than in lab test?
Yeah, so actually, right now, there is not much data on this, what would be the round trip efficiency, but there are projection on the numbers. And people are saying that the round trip efficiency is actually right now lower, which is 20 to 30% lower than LFP batteries. So yeah, there has to be more research on, firstly, like the sodium ion cells has to be developed more so that we can have a good practical numbers on this. But right now we don't have such practical numbers. These are only projections. Yeah.
Amazing. Thank you, Arshita. I hope that answers your question, Gerard. The next question we have from Malgor Zata. Great talk. That's an appreciation for you, Harshita. What potential do
Thank you.
you think sodium ion cells have in the future? Currently, max seems to be 160 kilowatt per kg from what you showed, but how do you predict its progression?
Yeah, so 160 watt-hour per kg at the cell level is the current energy density which sodium ion cells have from Faradion. But they have already announced that they are working towards 190 watt-hour per kg cell sodium ion cells. And BYD and CATL combinedly, they are also showing that 200 watt-hour per kg is possible with some of the chemistries of sodium ion batteries, especially if we talk about the layered oxide cathodes. So when we will be moving towards layered oxide from polyanionic from Prussian blue cathodes, so then it is possible that we can reach up to 200 watt per kg at the cell level. Yes.
Thank you, Arshifata, for that. The next question is thanks for the presentation. I'm wondering if you happen to know the anode and cathode materials of the sodium ion battery, let's say produced by CATL or BYD.
Right now, BYD and CATL are both buying their cathode materials. That's what I have, like the current information. That's what I have right now. But I am not sure about like what is the status on the anode side. So sorry for that. I cannot answer this thing. Yeah,
No problem. Um,
yeah.
Great. Let's keep the questions flowing in the chats. If you have any. Okay, another question from Arjun. The application of sodium ion batteries in EVs, would it be only for cars or could it even be used for two or three wheelers despite the energy density? Do you think it might be different in adoption in EVs in the India, Southeast Asia, and China, which is based on cost, climatic factors, etc., compared to either Europe or US? What are your thoughts on this?
Yeah. So actually, there are three questions. I'll start
Yeah,
with the first one. So if we see the so can you repeat the first one again, Priyal? I'm sorry. I
of
just
course, of course. The application of sodium ion batteries in EVs, would it be only for cars or could it be even for two or three
yes.
wheelers?
Yeah, got it. Yeah. So, if like people are already using these batteries for the four-wheeler electric vehicles, then it's like pretty much possible that we can use them in two-wheelers and three-wheelers because they require lesser energy density compared to four-wheeler cars. And the other question is, what about their applicability in different regions? I guess that's what you are asking, if I'm correct. So, if we see the temperature range in which sodium ion batteries can run, that is actually has a wider temperature range compared to what current lithium ion cells have. So there is no doubt like these type of batteries would be good for the countries where there is large fluctuations in the temperature throughout the year, especially Asia. And if we talk about Europe and USA, so there are some demonstrations of sodium ion cells where they have shown that we can also go till minus 30 degrees Celsius for the sodium ion cells. So I think these batteries can be applicable in the electric cars or two wheelers, three wheelers, or four wheelers in any type of region, like irrespective of the region where they will be used. Yeah.
Great. Thanks for that. Another question we have from Ayan. Anode and cathode, you have mentioned aluminum. Can we go for titanium as a current collector?
Actually, aluminium and copper are the best electronic conductors among all the current collectors that are available right now. So I am not sure about the electronic conductivity of titanium, but you have to compare it with their electronic conductivity and then you can find your answer. Yeah,
Hmm, that's true. Absolutely agreed on that.
yeah.
The next question is there any challenge of cell balancing? What are we usually facing in lithium ion batteries?
Yes, definitely. Because as I said, that the current state of the art anode is hard carbon, and you like everyone knows that hard carbon has an issue of poor initial Coulombic efficiency, and the interfaces that gets formed on the sodium ion cathode and anode side are also unfortunately not very stable. So there are definitely issues with balancing of the full cells, but if we can have some technology BYD is using right now for the Gotain is using right now, like the pre-lithiation studies, like studies they are doing on the silicon anode side, and because of that, they are able to make a balanced lithium-ion full cell. So if those type of strategies could come up in the future, then definitely the cell balancing problem can be sorted out. Yeah.
That's an interesting take. Um, Also, if we have, I think we have some time for a few questions as well. Another question we have: does parameterization of a sodium ion cell look similar to current lithium ion from a BMS perspective?
Yes, so like the cells which are there right now, they are exact. The parameters are exact copy of what people are using for lithium-ion batteries. So basically, for if we talk about the cylindrical cells, so people have used 26650, and the other one which I showed in my this thing, yeah, there's 32140 format, which are being used for lithium-ion cells as well. And if we talk about the BMS, so as I said, that BYD is already planning to have a hybrid type of system. So ultimately, they had to keep the parameters same for lithium ion and sodium ion cells to have a like uniformity in their battery pack. And in that sense, I guess BMS has to be designed like differently for this hybrid type of system. But I am not pretty sure about the BMS on the complete sodium ion battery pack side.
Okay. Another question we have from Derek. What
Yeah.
is the current path forward in improving sodium ion batteries cycle life? What are your thoughts on that?
Yeah, okay. Yes, that's a very good question. So right now, mostly the cathode materials that are being used, which are showing a good cycle life, are polyanionic and Prussian white, which have a very stable structure. And these can easily intercalate and de-intercalate sodium ions into their structures. But if we talk about this oxide-based cathodes, which have a higher specific capacity compared to polyanionic and Prussian white cathodes, these oxide-based cathodes face challenges of structural integrities during long-term cycling. So the best way right now to move forward is to improve the structural integrity of sodium ion cathodes, which have a higher specific energy. And the other thing is, like, the anode which we are using right now is the hard carbon, which has a low specific capacity compared to the alloy based or conversion based anodes. So we can employ them as well for the next generation of sodium ion cells to increase the energy density.
So
Yeah.
we have one last question from the audience. What are your thoughts on swelling of the cells?
Okay, so swelling of the cells, I guess you mean when we operate them at high temperature. Like, the question is not very clear to me, but probably you are talking about the same. So if we charge discharge our cells at higher temperatures, then there are chances that electrolytes can form lots of gases, can have lots of parasitic reactions, and because of that, lots of gas formation will be there, and the cells can swell up. So, but if we see a comparison between the sodium ion cell and a lithium ion cell, as I said, that they have a better thermal stability of their electrolyte systems compared to lithium ion cells. So the
Hmm.
selling problem should be lesser in sodium ion cells as compared to lithium ion cells. However, there are no exact studies on this thing right now for sodium ion cells. That has to be investigated more in depth, if like before giving any exact answer to it. Yes.
Perfect. Thank you very much, Harshita, for bearing with us with so many questions. You've been a
Yeah,
great
all
sport on
right.
that. But unfortunately, now we have to close. But if you have any more questions, feel free to reach out to Harshita via LinkedIn, or you can also write to Battery Associates and we can connect you as well. Um,
Sure.
Wonderful. With that, we can close the deep dive session for today. And I want to thank all of you for joining, taking your time out to attend the entire battery day. Harshita, I want to thank you as well for being a speaker for the event. It was great having you. We're
Thank you,
very
Priya.
proud that you could join us today. And absolutely a wonderful presentation from your end. But now, please
Thank
tune
you,
in to
Priya.
the stage for summary and key takeaways remarks for the entire battery day. We'll be summing up all the events, the panels, the discussions that has happened over here. And later, we'll also have a brief networking break as well. But thank you everyone for joining, and thanks, Harshita, once again.